So, as I told you, if you see the slide, the sputtering techniques can be divided broadly into 4 categories. One is DC sputtering, second is RF sputtering, third one is Magnetron sputtering, and fourth is reactive sputtering. Targets are available in variety shapes, examples are disc, toroid, plates, etc., and of course sizes. As the energetic ion strikes the surface of a material, there are 4 possibilities. One is ions with very low energy may simply bounce off the surface, right. If not energy, it will just bounce off. At low energy, the ion can be absorbed off the surface, generating heat. Above 10 kilo electron volt, you will be able to see that the ion penetrates into the material many atomic layer spacing, which is the ion implantation, and between these two ranges both energy transfer mechanism occurs and substrate atom or clusters of atom will be ejected from the surface of the substrate with energies about 10 to 50 electron volt. This additional energy provides sputter atoms with additional surface mobility to improve the step coverage of the. So, step coverage is let us say I have a material which is patterned like this. Okay. Now, this is some material and this is a substrate. When you generally go for thermal evaporation, what will happen that this step, there is this one, will not be covered properly. Okay. But in case of sputtering, this step coverage, that means this particular step will be covered properly. So, I want to deposit a film on this particular block. So, in this sputtering case, I will have some kind of proper step coverage mechanism, while in case of the thermal evaporation, it is the step coverage is poor. So, that is the advantage of sputtering, that they improve step coverage. When you talk about yield, yield will be number of sputter ions divided by number of incident ions. That means that how many number of ions are incident onto the target and respectively how many numbers of sputter atoms are ejected. So, that means if it is equal to 1, that means you have a better ratio. If it is greater than 1 also is better, but it is also the yield is also inversely proportional to lot of to binding energy. It is proportional to square root of energy of ions and proportional to ion and target atomic mass, and finally proportional to angle of incident and reduction in deposition pressure gives a better yield. So, several parameters are responsible for improving your sputter yield. The first one, like we discussed, is that it is inversely proportional. The sputter yield which is given by S is inversely proportional to binding energy. Second is it is proportional to the square root of the energy of ions. Then it is directly proportional to the atomic mass. Then it is directly proportional to the incident angle, and finally, if you reduce or decrease the deposition pressure, then your yield will be better. Okay. These are some of the schematics corresponding to that, and it is very easy to understand from the schematic itself, that is angle of incidence and sputtering yield, how it is decided, with ion energy and sputtering yield, how it is decided, and finally, if you have pressure and versus sputtering yield, as you can see that as you decrease the pressure, the deposition rate increases. In case of sputtering yield versus angle of incidence, you can see that at 60-70 degree you have a better angle, and at pi by 2 here that decreases, the sputtering yield decreases. At 60-70 you have a better sputtering yield. Finally, when you talk about ion energy, then you already know that it is square root of the sputtering yield is square root of the energy. So, let us quickly see 3 sputterings or 4 sputtering method. The first one is your DC sputtering. In DC sputtering you have a anode which is positive, you have a cathode which is negative, and then there is a ground shield of course, and water cooling, because there will be generation of heat. Now either you put the target on the top or you can put target on the bottom, it does not matter. The target is generally at the cathode is a negative, and then substrate is a positive. At low pressure the cathode shield is wide and ions are produced from the target. Mean free path of the detached atom is inversely proportional to the pressure. Mean free path is given by lambda. As the pressure is increased at fixed voltage, the mean free path is decreased, as you know, because if the pressure is increased means vacuum is decreasing. If vacuum is decreasing, that means from 10 raised to minus 5 it comes to 10 raised to minus 1, then the pressure is decreased, right. If the pressure is the pressure is increased. If the pressure is increased, then what happens is that mean free path would be poor. And more ions are generated. But the pressure is too high, the sputter atoms undergo increased collision scattering and are not efficiently deposited. The optimum condition is stated in the graph which is here. This is optimum condition, that is how much current should be applied versus how much argon pressure should be there. If you increase the argon pressure and you keep it around 800 to 140, then you have a maximum sputtering parameter in this case of non-magnetron sputtering. We are not talking about magnetron sputtering, this is just DC sputtering. It can be DC magnetron sputtering also, it can be RF sputtering, RF magnetron sputtering as well. So, in general deposition rate is proportional to the power consumed and inversely dependent on the electrode spacing. So, that means that if I reduce the spacing between this, deposition will be higher, if I increase it, deposition will be lower. RF sputtering. So, in case of RF sputtering, again you know that instead of DC you are applying a RF supply and there is a mass flow controller through which you can control the argon gas, vacuum through which you can create the vacuum, again you have your substrate and you have your target, and then there is a generation of plasma when you insert the argon gas. See, the principle remains same, only the way to bombard the argon gas onto the target, here it will be different because here we are using the RF sputtering method. The advantage of this sputtering method is it can be used very effectively for depositing insulating thin films or the films which are having greater than 10 raised to power 6 ohm centimeter resistivity. You understand the difference between resistance, resistivity, sheet resistance. So, R, rho and what is sheet resistance, how it is given, what is the unit of it, ohm centimeter. Okay. So, this again very simple things, but we do not take it further. We do not know the difference between resistance and resistivity, right. We even do not know how the resistance can be changed. What is the unit of resistance? Of course, we know it is ohms, right. How the if I increase the length, what will happen to resistance, if I decrease the thickness, what will happen to the overall resistivity of material. Can a resistivity of every metal will be different or it is same? See, of course it is different, right. The point is very basic questions are generally asked in the interview process to understand how good your basics are, of course with the application. So, have very strong basics, okay. So, that is my point, that you need to understand the difference between resistivity, resistance, piezoelectric effect, piezoresistive effect, Ohm's law, Richardson law, right, thermoionic effect, how it is governed. So, these very simple things. Okay. Cosine law. So, at AC signal above 50 kilohertz, electron oscillating in the glow region acquire enough energy to cause ionizing collisions, reducing the need for secondary electrons, and secondary RF voltage can be coupled through any kind of impedance, so that electrodes need not be conductors. That means that we do not have to have electrodes that can be conductors, because here we are using the RF energy. Also it is possible to sputter any material irrespective of its resistivity. Why? Because typically RF frequency employs about 13.56 megahertz, that has been reversed for plasma processing by Federal Communication Commission, which is FCC. So, this is reserved, okay. This is reserved for plasma processing, which is your 13.56 megahertz. Generally, you will find in the RF sputtering system, this is the frequency that people use. Now, in RF sputtering, the target cell bias is to negative potential and positive ion bombards away atoms from the subsequent deposition. As the target is capacitively coupled to the RF generator, metals as well as insulators can be deposited. So, the advantage of RF sputtering were the following. Now, if you talk about magnet and magnetron sputtering, what you see here is that in a magnetron sputtering, a magnetic field of strength B is superimposed on the electric field between the target and the substrate. So, when you have your magnet, then it will be superimposed onto this electric field. As you can see that electrons with dual field environment, which is given by Lorentz force. Lorentz force you already know, which is given by F equals to m dV by dt equals to minus q into epsilon plus mu by into B, where q, m and mu are the electron charge and mass and velocity respectively. First, let us consider the case where magnetic field and electric field are parallel as shown in figure A, which is shown here, okay. When the electrons are emitted exactly normal to the target surface and parallel to both the fields, then what will happen when you see the mu into B will become equals to 0, or electrons are only influenced by the electric field. See, when you have this equals to 0, that means what is the role? Only electrons are responsible for the field or influencing the field. Now, if we consider the case where electric field is neglected, but only magnetic field is still applied as shown in figure B, which is here, right. What will happen? The electron is launched from cathode with a velocity v at an angle theta with respect to B. It experiences a force which is given by this equation in a direction perpendicular to the magnetic field. And what will happen if that is the case? The electron now orbits in a circular motion like this. It keeps on orbiting in a circular motion with a radius r that is determined by centrifugal and Lorentz forces given by these equations, and the electron motion is helical with constant velocity which is given by this equation. If the magnetic field were not present, such off axis electron would tend to migrate. Now, here we are kind of managing the electron to be within the certain region, and that is why the deposition rate would increase. Further, if you see, the magnetron motion of electron is helical and with respect to radius, but because of the acceleration of electric field, the pitch of helix strengthens with time, and because the pitch will strengthen with time, what will happen? There will be more bombardment of the ions onto the target, resulting in a dislodging of atoms faster. When you have higher dislodging of atoms, your deposition rate increases, your deposition rate improves. Okay. Now, let us go to the last one, which is a reactive sputtering. In reactive sputtering, thin films of compounds are deposited. So, not only just one film, but multiple films you can deposit, or compounds can be deposited. For example, if you want to deposit aluminum oxide, or you want to deposit indium oxide, or tin oxide, or indium tin oxide, or silicon dioxide, or titanium nitride, titanium nitride, aluminum nitride, silicon nitride, or you want to deposit titanium carbide, right. You want to deposit copper sulphate, zinc sulphate, you want to deposit oxycarbides like titanium, tantalum, aluminum and silicon. All these things are possible if we go for reactive sputtering. Why? Because on reactive sputtering, thin films of compounds are deposited and substituted by sputtering using metallic targets in presence of reactive gas in chamber, usually mixed with the inert gas, and irrespective of which of these material is considered during reactive sputtering, the resulting film is either solid solution alloy of the metal doped with reactive element, a compound, or some mixture of two. So, either it can be just this is a mixture, or it is a alloy, or it is a compound. So, in bias sputtering, electric fields near the substrate are modified in order to vary the flux. It is a game of improving the flux, modifying the magnetic field, modifying the electric field, and to improve the the way you dislodge the atoms. So, a target voltage of about -1000 to -3000, while a bias voltage of -50 to -300 is applied. Due to charge exchange processes in anode dark space, very few discharge ions strike the substrate. The technique has been utilized in all sputtering configuration, that is bias sputtering is used whether you use DC, RF, magnetron or reactive sputtering to alter broad range of properties of the deposited film. Depending on the film that you want to deposit, the bias voltage and the target voltage are modified. This technique helps to tune resistivity, stress, dielectric properties, optical properties. So, people who go and understand the thin film physics and thin film electronics and thin film deposition techniques, they have to play with this particular parameter, how we can improve the stress of the film, how we can change the dielectric properties of the film, how we can improve the optical properties of the film, how you can tune the resistivity of the film. So, if you want to do that, then you have to change the parameter like bias voltage, like your target voltage. Okay. So, this sputtering helps you to change those parameters, and that is why it is a good technique to improve the overall quality of the film. So, if you see the slide, it is same thing that we are discussing from previous slides, that sputter deposition you either go for DC sputtering, and here you can see there is a heater, the electrode, wafers. Now, what is the role of this heater? You see, when you have a heater, then when you deposit the atoms onto this substrate, they can align it. So, instead of getting a amorphous film, we can get a polycrystalline film. This advantage of heating the film during deposition is to improve the crystalline property of the film. Now, plasma is needed to make the gas conductive and generate ions can be then accelerated to strike the target. We know that higher pressures than evaporation about 1 to 100 millitorr, better at depositing alloys and compounds than the thermal evaporation. And if you see this is the system that it looks like the which is the RF sputtering system, and do not worry about the complexity of system how it looks. When you operate it, it is not that difficult. Of course, you want to design one, you need to take care of lot of other parameters, but fortunately you will just operate the system, you are not in the designing of this particular system, right. But you should know each and every part of this system. So, for example, like I said QCM, right, how we know the pressure. So, for the pressure which is less than 10 to the power minus 3 torr, we can use Pirani gauge. For pressure which are about 10 to the power minus 3 torr, which is minus 4, minus 5, minus 6, minus 7, you have to go for Penning gauge. So, what are those gauges? What are the principle of using those gauges? On which principle those gauges are operated? This all things we have to understand. But anyway, there is a totally different topic, do not worry about it. You understand that sputtering is a way to deposit a film, and in sputter deposition is done in vacuum chamber, you already know that, right. Rest of the points we already discussed, so I do not want to rediscuss these things, except that you can see that there is an excellent step coverage, sharp topologies because of a higher chamber pressure, and film stress can be controlled to some degrees by chamber pressure and the RF power. So, that is very important parameters. Now, if I want to further understand, then you can see that these are the some of the targets that are used for sputter deposition, and the major operating parameters, as now you already know, would be your operating pressure, or it can be power, DC sputtering, voltage, substrate bias, substrate temperature, and in addition to IC industry, a wide range of industrial products are using sputtering. For example, LCD, liquid crystal display, your computer and hard drives. If you see the CD, you will see the coating, and that coating is using the sputtering. You will see that hard coating for tools, metals on plastics, and many more. Of course, it is more widely used for industry than evaporator. In industry, sputtering is preferred over evaporator, partly because for the evaporation there are very few parameters that one can control. Second, the step coverage is poor. Third, it is not suitable for compound or alloy, and finally considered materials are deposited on the walls and wasted. In case of sputtering, that is not the case. So, if I want to consider advantages and disadvantages of sputtering system, I can consider these advantages. First is that in sputtering, a large size target can be sputtered with a uniform thickness over large wafers. Film thickness can be controlled, control of alloy composition, step coverage, grain structure can be done. Sputter cleaning of the substrate in vacuum prior to film deposition is possible. Device damage from X-ray generated by electron beam is avoided, because in case of electron beam, if I incident an electron beam, there is a generation of X-rays, we know it, right, in physics. So, if I want to avoid those X-rays, then I would go for sputtering. However, like every system, sputtering also has some limitations. The first limitation is it's expensive. The second limitation is that the deposition rate for some material like silicon dioxide, it is extremely low. The third limitation is materials such as organic solids are easily degraded while during the ionic bombardment, and finally greater probability to introduce impurities in substrate because it operates under a high pressure. So, let us say advantages and disadvantages of PVD. Okay. Now, until you know CVD, it is very difficult for you to understand what are the advantages of PVD over CVD. However, since we do not require to go in detail about CVD in this course, I will just tell you CVD stands for chemical vapor deposition. Alright, chemical vapor deposition. So, there are certain advantages of chemical vapor deposition and there are disadvantages. The PVD has advantage like high deposition rates compared to CVD, and one biggest advantage is that there are no harmful exhaust. In chemical vapor deposition, the byproducts are generally exhaust and which are harmful in nature. While the limitation of the PVD compared to CVD is that uniformity in CVD is better, in PVD it is not as great as CVD. Of course, sputtering is better than thermal and E-beam, but it is not as good as the chemical vapor deposition. And finally, the step coverage of the CVD is better, and in the PVD step coverage is poor compared to CVD. Again, if you just compare PVD, sputtering is better for the step coverage, but if you compare PVD versus CVD, CVD is better for the step coverage. Finally, you can see here, if I want to compare the evaporation and sputtering with different parameters, then I can say that when you talk about rate, the evaporation is faster, when sputtering the evaporation is slow, choice of materials in evaporation is limited. In case of sputtering, you can almost sputter everything. Purity is better here in sputtering, it is of low or medium, because low or medium vacuum range there is a possibility of incorporating impurities. The substrate heating is very low in this case, unless you use magnetron, if the substrate heating can be substantial. Surface damage very low, but electron beam damage is possible. In this case, the possibility of surface damage is because of the ion bombardment, while in situ cleaning when thermal evaporation is not possible, but it can be easily done by sputtering. You can clean the chamber by using sputtering itself. Alloy composition, little or no control, you can here in sputtering you can deposit alloys. Finally, there is X-ray damage is there in E-beam, in radiation and particle damage is possible, but not because of the X-ray. Challenge in source material, it is easy, this is expensive as we already have discussed. Decomposition of material is low in case of sputtering. Scaling up is very good, it is difficult in case of evaporation. Uniformity also is difficult in evaporation compared to sputtering, because sputter can be used to cover large substrates areas. Number of deposition, only one deposition per charge, when in the case of sputtering there can be many depositions. Of course, when the capital equipment one time installment cost is more expensive for sputtering over thermal evaporation. Thickness control not so easy, in this case several controls are possible. The adhesion to the adhesion means what, how good your film is stuck on to the substrate. So, how good your film is adhesive to the substrate. In this case, in the case of sputtering, the adhesion is excellent, while in case of thermal evaporation it is poor. Shadowing effect is large, in the case of sputtering shadowing effect is small. And finally, you can change the film properties very easily, because we have control, it can be controlled by bias, we have a pressure to change, there is a substrate to heat, there is a bias voltage, and target bias also is different. So, we can change multiple properties of the film while using sputtering, while in case of evaporation it is difficult to control. So, if you want to summarize the PVD techniques, then how you can summarize that, you can say that PVD is a technique which is based on the formation of vapor of the material to be deposited as a thin film. Finally, the material can be in solid form, which is generally heated until it evaporates. Either you use thermal evaporation or you use E-beam evaporation, or you can sputter it using the ions. In this case, we generally use argon gas to bombard the target, and the sputtering ions are generated by plasma discharge, usually within an inert gas, like I said, which is argon. It is also possible to bombard the sample with an ion beam from an external ion source. So, finally, this will allow to vary the energy and also ions reaching this target or the substrate, right. When the ions reaches the target, the atoms dislodges and falls on the substrate, and so how we can change the thickness of the film. So, the idea here is that how you can deposit film onto a substrate using physical vapor deposition techniques. This is what we have covered in last 2 modules, including this one. So, let us see now as an example in the next module how to take a substrate, grow oxide, deposit a film using one of this technique, pattern it to form a patch that can be used for several applications. We will take this in the next module. Till then, you look at this module once again, understand the concept. If you do not understand anything, please ask us through the NPTEL forum. I will also have one more video where we will show it to you how to operate an electron beam and a thermal evaporation system that we have in our clean room, which is class 1000 clean room in the department, and that will little bit help you to understand further of how a film is deposited onto a substrate. We will show you that as an experimental laboratory module and you will be able to understand it further in a better way. Till then, you take care. Do let us know if you have any trouble through the forum, and I will see you in next module, which will be the last module on the instrumentation side, covering the photolithography, but using the PVD techniques. All right. Till then, you take care. I will see you in next class. Bye.